Okay, so far we have studied the electromagnetic radiations, electromagnetic spectrum, and the energy wavelength relation. Okay, and we also studied the line spectrum of the hydrogen atoms. Now, next topic is the Bohr model. Okay, so this is even better model. This accurately describes the hydrogen atom. So, and we will study two things. So, we will describe the Bohr model, what the Bohr model for the hydrogen, because Bohr model is mostly accurate for hydrogen single electron atom, then the multi-electron. So that's why for the multi-electron atom we will go to the quantum mechanical model. Okay, and we will use the Rydberg equation to calculate the energies of light emitted or absorbed. Okay, so now first of all, let's see what the Bohr models, before the Bohr model, what has been developed for the atomic models. Okay, so prior to the Bohr model, it has been considered that the atoms consist of the tiny dense nuclei surrounded by lighter and even tinier electrons constitutively moving around the nucleus, right? So before the Bohr, we assume that there is a nucleus. Around the nucleus, same as like the solar system, right? Around the nucleus, there is a tiny particle which moves around that and revolve around that. This classical mechanical description of the atom is incomplete, since an electron moving in an elliptical orbit would be accelerating, right? If the electron moving in the elliptical orbit like the Earth, then it should be accelerating. So according to the classical electromagnetism, the electron should continuously emit electromagnetic radiation, right? And this loss in the orbital energy should result in the electron's orbit getting continuously smaller until it spirals into the nucleus. Now, so before that, before Bohr, what has been considered is like this. This is the nucleus, this is the electron. Okay, so if that is, then what happens is this electron is, according to the classical theory, electron continuously emit the photon. Okay, and if that continuously emit the radiation, then its energy will be decreasing because some energy will go in the form of the photon. So what will happen is, first revolution is this, second revolution will be like this, okay, third revolution will be like this, fourth revolution will be like this, fifth, eventually it will collapse into the nucleus, right? It should collapse into the nucleus if that is true, right? That's why that's the reason this is not true. So electron never collapse into the nucleus, right? So Niels Bohr attempted to resolve the atomic paradox, but that's the atomic paradox, right? By ignoring classical electromagnetism prediction that the orbiting electron in hydrogen would continuously emit the light. So the Niels Bohr, he has a very tremendous contribution in the science, especially the physics and chemistry. The Niels Bohr attempted to resolve the atomic paradox by he ignored that classical electromagnetism prediction, which predicts the electron continuously emits the photon. He ignored that, and he gave the new prospect, and that is he gave the new atom model, and that is the Bohr's atom model. Okay, so what is the Bohr atomic model? Bohr incorporated that the following into the classical mechanics description of the electron. So yes, he added something in the classical description of the electron. Okay, so one is he incorporated Planck's idea of the quantization, right? E equals to nh nu, right? This is the Planck's idea of the quantization. Okay, so Einstein's finding that light consists of the photon whose energy is proportional to their frequency. So he again he considered the Einstein's finding. So the photon's energy is proportional to the frequency. So that's why E equals to Planck's constant times nu. Okay, so that's why this is the Einstein's finding. Energy of the light is proportional to its frequency. That's the Einstein's finding. Okay, so Bohr assumed that the electron orbiting the nucleus would not normally emit any radiation. So what the Bohr assumed? No, it doesn't emit any light. When it orbiting on the nucleus, it doesn't emit any light. That's why it don't spiral and collapse into the nucleus, right? So rather the electron emit or absorb a photon, it moved to a different orbit. Assume that. So once it gets the energy, it moves to the different orbit. It don't emit the light, but it moves if it get the energy, then it will move to the different orbit. If it emit the energy, lose the energy, it orbit in the another. For example, let's say this is the neutron, proton nucleus. This is the electron. So if you give the electron, it instead of radiating energy, it will move in the another orbit. But if this orbit electron is in that orbit, that higher orbit, if it lose the photon, then it will go to the another orbit. Just changing the orbits. When it emits the photon, then it's just changing the orbit. So that was the Bohr model. The energy absorbed or emitted would reflect the difference in the orbital energy. So he said that, so this is the nucleus, this is the first orbital, this is second orbital, like that. Okay. So if you give the energy, electron will jump back to here and it will revolve on the another orbit. And if it lose the energy, it jump back to the ground state and revolving in the another orbit. This is the Bohr model. Okay. So the energy absorbed, how much energy it emit or it absorb. So how much energy it will emit or absorb equal to this. The change in energy equals to energy of this final orbit. This is the energy initial orbit. So change in energy delta E is equals to modulus of the absolute value of delta E is equals to energy of the final orbit minus energy of the initial orbit. That's it. And that is equals to Planck's constant times nu. So according to the Bohr, the change in the energy, how much photon it can radiate or how much energy is absorbed or how much energy it radiate out is equals to energy of the final orbit minus energy of the initial orbit, but that is equals to Planck's constant times frequency of that emitted photon. So what is the photon emitted here? It's the frequency times h nu. The Bohr is finding that, and the h times nu equal to c by lambda. So according to the Bohr, so if the electron is here, if you give the energy, it will jump to the another level and it will be started revolving in the another level. And how much energy is absorbed here? How much energy this electron has absorbed? That is, what is the energy of this level and what is the energy of this level. Subtract these two, that much. And that much equal to that difference in the energy. That difference in the energy is equals to Planck's constant times the frequency of that absorbed energy wave, right? And suppose the electron is here, it jump back to this one, then it will radiate a photon. It will give a photon. So what will be the energy of this photon? Means the absorbed photon, means the emitted photon is equals to, again, change in the energy of this, difference between energy of this level minus energy of that level equals to the h times Planck's constant times frequency of that photon. So that is his finding. So Bohr's finding. So the Bohr's expression for the quantized energy is this. That's why En is equals to minus k by n square, where n is equals to 1, 2, 3, and so on. K constant comprise fundamental constants such as the electron mass, charge, Planck's constant, etc. Okay. So now inserting the expression for the orbital energies. So En, so look at that, En is equals to minus k by n square, right? So what will be E delta E is equals to Ej minus E final minus E initial is equals to E final will be, for example, N1. Let's say E final is N2. Let's say this is the level. Okay, this is another level. This is N1 level. This is N2 level, right? So look at that. En means E2. So delta is equals to E. Let's say this is 1. This is level 1. This is level 2. E2 minus E1 is equals to E2 will be minus k by n2 square, minus E1 will be minus k by n1 square. So if you simplify that, you can have this result, right? Delta E is equals to k times 1 by n1 square minus 1 by n2 square, and that its value is Sc by lambda, right? Lambda is the wavelength of that light, whatever it produces. Okay, so now this is k. Okay, so let's see that the just simplify that. Okay, so we have the k 1 by n1 square minus 1 by n2 square is equals to hc by lambda, or 1 by lambda equals to, then take out this and divide by sc here. Okay, so this is 1 by lambda. 1 by lambda is equals to ksc by 1 by n minus 1, this result, okay, this value. So this is the value. So that's why after you simplify that, you will get this one. You will get this value. Okay, so this is the lambda, 1 by lambda. Take the sc in the other side, and this one. Okay, which is identical to Rydberg equation. So Rydberg equation was R infinity is Rydberg constant is equals to k by hc. This is similar as like k by hc. See, k by hc, right? So k by hc. This is the Rydberg equation for R infinity. Okay. So now one of the fundamental law of physics is that the matter is most stable when it has the lowest possible energy. Last time we see that this is one energy, this is the nucleus, this is the first energy level, suppose this is second, third. So lowest energy level is said to be the ground state. Okay, that is said to be ground state, and all others are said to be the excited state. So I may ask you in the exam what is the ground state and what is the excited state. Okay, so I can give you the energy to calculate energy of the ground state also by giving some parameters. Okay, so now when the atom absorbs energy as a photon, the electron moves from orbit with a lower n to higher n, right? We already discussed that. So when the electron falls from orbit to the lower one, it emits the photon. We already said that. Since delta E, change in energy, so change in energy can only be discrete value, the photon absorbed emitted only have a wavelength with a discrete value. So you cannot have the continuous value, right? N equal to 1, n equals to 2, n equal to 3, like that. So it has only the discrete value. So no between them, right? 1, 2, 3, no 1.5, n equal to 1, 2, 3, 4, like that. So now let's see this one pictorially. So this is the ground state, n equals to 1. If jump to the another one, these other states are excited state, and energy will be increased. Ground state has the least energy, this has this much energy, this has this much energy, like that. Okay, these other states are excited state, and once it jump up, it can jump back also, and it will radiate the photon. How much? If you jump back, it radiates the photon. It's jumping from second state to third, is second excited state to, it's going to the fifth and third, fourth, fifth, and it's jumping back, it will radiate the photon. So now let's see one example. Okay, and this is the example important for exam also. Okay, so what is the energy in joule and the wavelength in meter of the line in the spectrum of hydrogen? It's saying about the hydrogen that represent the movement of the electron Bohr orbit when n equals to 4 to n equals to 6, right? So this is the formula. Delta E is equals to k, right? Delta E is equals to k 1 by n1 square minus 1 by n2 square. So n1 equals to 4. See, n1 equals to 4, n2 equals to, yeah, n2 equals to 6, right? So n2 equals to 6. The difference in energy between the two states is given by the expression. When k is this, the value of the k is this. This is the value of k. Just to plug in here. Okay, let's see that. Just to plug in here, right? So delta E is equals to k 1 by n1 square minus 1 by n2 square. That's it. This is the value of k. N1 is 1 by 4 square minus 1 by 6 square, and this is the value. This is the energy. Okay. So this difference in energy position indicates a photon enters system is absorbed to excited the electron from n equals to 4 to up to the n equal to 6, because this is not negative. That's the reason. Okay. The wavelength of the photon can be calculated by this one. So what will be the wavelength of the photon? Just to plug in the value of delta E hc and you will get the lambda. Okay. So delta E is this value, right? So let me go to the next slide. Okay. Yes. Delta E is equals to lambda equal to hc by delta E then, right? Because delta E equals to hc by lambda. That's why you can crisscross, and the lambda is equals to hc by delta E. That's the reason. H is the Planck's constant. This is the value. C is the velocity of light. This is the value. And delta E, we just found that. This is the delta E. So that's why this is the this much meter. Lambda wavelength is equal to. Okay. So this is the infrared region, right? 10 to the power minus 6 meter means infrared region. This is in the infrared region. Okay. So now let's see the limitation of the Bohr model. Bohr model is suitable for hydrogen, but the many electron system it don't. Okay, Bohr was unable to extend his theory to the next simplest state of helium. Hydrogen atom it works, but the helium don't work, right? Bohr model was severely flawed since it was still based on the classical mechanics. Okay, it is not in the quantum mechanical base. It is still based on the classical theory. Okay, that's why it has still some flaws. So that's why Bohr model don't work. It works very nicely for the hydrogen atom, but it don't work for the many electron system like helium, lithium, like that. After hydrogen, it don't work. That's why a new theory developed. That is the quantum theory, and we are going to study this quantum theory. Okay, so we will study about the quantum theory, and in this quantum theory, we will study the 4 quantum numbers, and then after 4 quantum numbers, we will study the electron configuration, and this chapter will be end then. Thank you, and let's see. We will in the next slide we will go to the quantum theory.